$90 billion, exactly the annual valuation of the global industrial fastener empire. Giant bolts and nuts represent the most critical components of this massive market, serving as the primary elements that secure the entire modern industrial infrastructure. Why are these components treated with such extreme technical rigor during their creation? At first glance, they might appear to be simple pieces of steel with machine-cut threads, but in reality, every unit is a highly engineered product resulting from a complex cycle of metallurgy, high-pressure forging, thermal heat treatment, and uncompromising mechanical testing. A single deviation in the quality of the raw material, a microscopic error in geometric shape, or an inconsistency in tightening force can compromise the safety of an entire structural joint. One can notice how the manufacturing cycle for these large-scale fasteners begins with a uniform and foundational procedure. This involves the systematic cutting of raw steel billets. High-strength alloy steel, rolled into large-diameter round bars, is fed into industrial cutting units to be divided into segments of strictly controlled length and mass. Modern systems utilize either hydraulic shears or high-power industrial saws to achieve flat, square cuts that do not compromise the internal grain structure of the metal. The equipment gradually moves the steel forward as a liquid coolant is sprayed directly onto the contact zone. This continuous stream reduces thermal buildup, minimizes friction, and effectively flushes away metal chips from the blade. It is visible how this process keeps the cutting tool stable while ensuring the surfaces of the billets remain free from any thermal damage or distortion. But this is just the beginning. Typically, the billets destined to become bolts are approximately twice as long as those intended for nuts. This is because the bolt manufacturing process requires a greater volume of material to forge both the load-bearing shank and the hexagonal head. The process is only gaining momentum as the machines continue their work. In a single production shift, each individual cutting station processes thousands of billets for both fasteners. Each specific cut is completed in just a few seconds, yet the allowable tolerance for error remains extremely small. This precision is mandatory because the final shape and the ultimate mechanical strength of the fastener depend entirely on the initial dimensions established during this first stage. The raw steel segments are now prepared to move toward the forging hammers to undergo their primary transformation. 1900 to 2100 degrees Fahrenheit is the precise thermal range required to prepare steel for the forging process. Why does the method of applying this intense heat differ so significantly between a nut and a bolt? At first glance, both fasteners appear to be simple steel components, but the physics of their structural formation demands two entirely distinct thermal strategies. For nuts, the entire steel billet is fed into a continuous furnace where it undergoes uniform heating throughout its entire mass. This process is only gaining momentum. Full-body heating ensures the billet reaches a completely plastic and homogeneous state. This state is critical because it allows the metal to flow evenly inside the die during the high-pressure forging stage. One can notice the billet shimmering with heat as it achieves the consistency needed to form a solid hexagonal body before the internal hole is drilled and threads are subsequently cut. The temperature is monitored with extreme precision to prevent the outer surface from burning while guaranteeing the core remains sufficiently soft for deformation. Bolts are processed in a different way. Instead of heating the entire length of the steel bar, only the front section passes through a localized induction heating system. Within a span of just a few seconds, the head portion reaches forging temperature and begins to glow a bright orange red. The shank, located behind this section, remains significantly cooler throughout the operation. It seems simple, but in reality, this localized heating method concentrates energy exactly where the hexagonal head must be formed. This strategy reduces overall energy consumption while preserving the mechanical integrity of the bolt shank, which serves as the primary load-bearing section of the fastener. The equipment gradually moves the heated billets directly into the hot forging area for immediate shaping. For the production of nuts, the uniformly heated billet is positioned inside a closed forging die. A high-capacity hydraulic press descends with immense force, compelling the plastic metal to flow into the specific geometry of the mold. Under this intense compression, the metal is compacted and the internal crystal grains rearrange into a tighter, more resilient structure. It is visible how the metal becomes denser and more uniform under the weight of the press. Everything only gets more complicated. Alongside each pressing cycle, the forging die is sprayed with a specialized layer of high-temperature coolant and lubricant. This liquid helps control the extreme heat, reduces mechanical friction, and protects the surface of the die during continuous high-speed operation. The forging process for bolts focuses exclusively on the induction heated head section. The billet is positioned so that the glowing hot end sits precisely inside the die cavity. As the press applies force, the metal is forced to flow outward to form the hexagonal head shape. At the same time, the die is sprayed with the same high-temperature lubricant used in the nut forging line. One can notice how the liquid instantly evaporates upon contacting the hot die, creating a temporary protective film. This vapor barrier prevents the metal from sticking to the mold and ensures that every bolt head is shaped cleanly with sharp, well-defined edges. Transition to the next level. Immediately following the forging stroke, both the bolts and the nuts are discharged directly into large steel containers. They are left to cool naturally in the open air. For large-size components, this cooling stage typically lasts between 30 and 60 minutes, though the duration can increase if the total steel mass is especially large. This slow cooling method is employed to avoid thermal shock and minimize the risk of microscopic cracking. It ensures that both the external shape and the internal metal structure remain stable before the parts move on to the next stages of production. The material is ready to move to the next processing phase without haste. 100% cooling must be achieved before the steel bolts and nuts are transferred to the surface cleaning stage. Why is this mechanical scrubbing of the metal surfaces so critical for the entire production chain? At first glance, the parts seem ready after forging, but in reality, a layer of burnt scale and oxidation clings to the metal, which would destroy precision tools in later stages. The cleaning removes these impurities to ensure dimensional accuracy. Boulders of metal parts are loaded in bulk into rotating drum cleaners or large vibrating barrel machines. The equipment moves slowly and with mechanical rhythm, ensuring that friction is distributed evenly across every square millimeter of the bolts. It is visible how the hexagonal edges are sharpened and the surfaces become uniform, dry, and silver gray. Everything only gets more complicated as the volume of the batch increases. From several hundred to several thousand individual parts fill the drum during a single cycle. The tumbling duration is not fixed, typically ranging from a few minutes to several tens of minutes. This timing depends entirely on the physical size of the components and the thickness of the oxide scale adhering to the steel. The process is only gaining momentum. One can notice the clean surfaces as the parts are discharged, now completely free of thermal defects. This preparation significantly reduces the wear on machining tools used in the subsequent phases of the manufacture. Transition to the next level. The clean parts move immediately to the identification marking station. Markings for nuts are stamped directly into the flat planes of the hexagonal body. For bolts, the symbols are placed exclusively on the top face of the head. These characters represent the strength grade, technical standards, and the specific manufacturer's code. It only looks obvious to label them, but in reality, these markings act as a mandatory identity card required for any part used in heavy machinery or large-scale construction projects. 30 millimeters or more can be the diameter of the shank as the parts enter the thread machining phase. Why is a light finish turning required before the threads are actually formed? The shank must have an exact diameter and a smooth surface to prevent defects during the rolling process. On the lathe, the bolt is clamped firmly and rotates at a perfectly stable speed. The cutting tool only skims the surface of the rotating billet to correct any minor dimensional deviations. But this is just the beginning. The smooth billet is then transferred to the thread rolling machine for the final transformation. One can notice how the bolt shank passes between hardened rollers that carry the negative profile of the thread. The metal undergoes plastic deformation, forced to flow under extreme pressure as each thread gradually rises on the surface of the steel. In a span of just a few seconds, the smooth shank becomes a full thread system that is sharp and uniform. It gets more complex further on. For the nuts, the threads are generated inside the central hole using high-power tapping machines. The tap rotates and advances through the central bore, progressively cutting the helical profile from one end to the other. The nut remains clamped in a fixed position while the tool moves along the central axis. This ensures perfect concentricity and a consistent depth for every internal thread. A continuous flow of lubricating and cooling fluid is directed exactly into the machining zone. One can notice how the fluid reduces friction between the rolling dies and the bolt surface, preventing damage to the finish. For the nuts, this liquid serves the dual purpose of cooling the tap and flushing away sharp steel chips. The process does not end at this stage. Thanks to this controlled cooling, the external and internal threads achieve the high level of dimensional accuracy required to carry heavy industrial loads. The material leaves the machining station, transitioning into a calm stage where the components are fully ready for the final tightening tests. Thus, the steel reaches the standard ready for the further stage. 100% precision is the standard standard against which every structural fastener is measured once the thread machining phase concludes. This critical transition marks the beginning of the rigorous quality inspection stage, a process that separates simple metal parts from components capable of supporting immense industrial loads. Why is such a demanding examination conducted at this specific point in the sequence? The machining process itself can introduce subtle variations in the material. A one-sentence delay ensures the focus remains on the structural integrity of the metal, because even a microscopic flaw in the thread profile could lead to catastrophic failure when the bolt is subjected to thousands of pounds of pressure in the field. Geometrical checks are initiated first to confirm the physical dimensions of the components. One can notice how inspectors measure the diameter, thread pitch, and thread depth with specialized tools to ensure every millimeter aligns with the design. Concentricity and the sharpness of the thread profile are evaluated with equal intensity. The equipment gradually matches the threads against standard gauges to verify a perfect fit. Even a very small deviation in these measurements leads to immediate rejection of the part. But this is just the beginning. Mechanical testing follows to probe the internal strength of the steel. Surface hardness, tensile strength, and torque resistance are tested under conditions that simulate extreme operational stress. Only after successfully passing every one of these trials are the bolts and nuts moved to the packaging stage. It is visible how the products are no longer classified as semi-finished parts, but as complete structural components. They are now prepared for transport to construction sites, power plants, steel bridges, and drilling platforms. In these environments, each bolt and nut will be responsible for holding massive industrial systems together under constant tension. It gets more complex further on. How is the steel that serves as the starting point for these giant bolts and nuts actually produced? One can notice the transition as the focus shifts to the raw material. Once the iron ore has been ground into a fine powder, the journey of purification begins in earnest. The mixture is blended with water into a thick slurry and directed into massive flotation cells for chemical separation. The process is only gaining momentum. The key to this purification lies in flotation reagents, which are surface active chemicals added with precise control to the mixture. These agents render the iron-bearing particles hydrophobic, causing them to repel water, while silica, clay, and other impurities remain hydrophilic. At first glance, the bubbling liquid seems chaotic, but in reality, it is a highly controlled chemical environment. Compressed air is continuously pumped from the bottom of the cells, creating millions of microscopic bubbles that rise through the slurry. These bubbles attach themselves to the chemically tagged iron particles, lifting them upward. The ore gathers into clusters, forming a thick reddish-gray froth that floats to the surface. Meanwhile, the worthless gang sinks steadily to the bottom, completely separated from the valuable material. This iron-rich froth is carefully skimmed off by automated manipulators and collected through multiple cycles of concentration. This refinement produces a concentrate with iron content often exceeding 65 to 67%. This is more than twice the concentration of the original raw ore. It marks a critical turning point where unshaped stone is reborn as a refined resource fully prepared for the demanding metallurgy ahead. The iron-rich slurry is then fed into vacuum filtration systems, typically drum or disc filters for dewatering. Why is the water content so strictly reduced? The mixture appears uniform, but excessive moisture would hinder the next heating stage. Under the pull of strong pressure differentials, water is drawn out, leaving behind a fine ore filter cake. This step significantly reduces the moisture content, ensuring the material is better prepared for the pelletizing and subsequent firing processes. Efficiency is maintained by these mechanical systems as the material dries. It does not end at this stage. From the filtration tanks, the iron concentrate emerges as a fine, dry powder, red as dust. In this loose form, it is far too fragile to be fed into a blast furnace without risking loss of material. To solve this, the powder is mixed with a measured amount of water and binding agents before being poured onto giant rotating discs. These discs are tilted at a specific angle, causing the material to tumble under gravity. With each steady turn, the tiny grains begin to roll and cling together, growing in size and rounding out. Millions of fresh pellets, uniform and spherical, are formed as the discs continue their rotation. These young pellets take on a distinct reddish-brown hue, but are still soft and delicate at this stage. One can notice the even layer of pellets forming on the surface as the machines operate. These components must endure further stages of processing to gain the strength and hardness required to withstand the fiery heart of steelmaking. The material is ready to move to the next processing phase without haste. 1,350 degrees is the maximum temperature reached within the rotating thermal chamber. Why must the iron ore pellets endure such extreme heat for dozens of meters? It seems simple to just heat the material, but in reality, uneven temperature distribution would leave the core core of the spheres fragile and prone to cracking under industrial pressure. This thermal treatment ensures that every single particle is baked uniformly from the center to the outer shell. The massive steel cylinder stretching across the facility at a slight incline rotates slowly on its horizontal axis. One can notice how the glowing red pellets tumble and roll in a constant rhythmic motion as they move toward the discharge end. Inside this colossal drum, flames erupt from the kiln's mouth and sweep through the entire length, creating a blazing river of heat. But this is just the beginning. Everything only gets more complicated as the ore reaches the end of the rotating drum. Residual dust and unwanted impurities are vaporized and burned away by the intense atmosphere. The once fragile spheres fuse into a dense, solid structure clad in a toughened exterior shell. It is visible how the resilient material exits the chamber, transitioning from a delicate state into a hardened resource ready for the cooling stage. The process is only gaining momentum. 2000 degrees is the threshold where the chemical transformation of the raw material truly begins. Once the iron ore has been pelletized, it joins forces with blazing hot coke that has arrived fresh from the ovens. These materials, along with limestone, converge at the summit of the blast furnace. It only looks obvious to mix these elements, but their precise layering determines the efficiency of the entire melt. Inside the towering structure, a powerful blast of hot air is injected from the base, causing the coke to ignite with fierce intensity. Carbon monoxide is released during this ignition, stripping the oxygen from the ore and reducing the solid mineral into streams of glowing molten iron. But such industrial power comes at a price in the form of environmental impact. Massive volumes of carbon dioxide, fine particulate dust, and noxious gases escape from the furnace mouth. This core step of metal production stands as one of the largest single sources of industrial pollution on the planet. The liquid metal does not stay in the blast furnace for long. One can notice how the molten iron, still radiating a blinding red heat, is transferred directly into the basic oxygen furnace. This colossal steel vessel is lined with thick refractory bricks to withstand the internal violence of the purification process. From above, a massive lance descends into the vessel, blasting a jet of pure oxygen at tremendous speed onto the liquid surface. The oxygen ignites instantly, stripping away carbon and remaining impurities in a chaotic display of energy. Pillars of flame and bursts of smoke surge high from the mouth of the furnace amid a roar of blinding sparks. At this exact moment, brittle pig iron is transformed into steel that is cleaner, tougher, and significantly more versatile. This is the point of rebirth where the crude metal evolves into a foundational material for infrastructure. And this is not the limit. The steel must be given a physical form before it cools. Immediately after purification, the liquid is channeled into continuous casting machines. One can notice the streams of liquid steel pouring into water-cooled molds where they begin to solidify into billets, slabs, or blooms. This stage represents the first tangible form of the metal. From these semi-finished shapes, the journey of transformation continues as the sections are reheated and sent through colossal rolling mills. The steel passes under massive rollers weighing dozens of tons, which exert incredible pressure to reshape the material. Thick slabs are stretched into thin sheets, while blooms are drawn into massive coils, and square billets become long, slender bars. With every successive roll and press, the metal moves closer to its final destiny. It is visible how the material takes the shape of the skeleton for a skyscraper, the span of a bridge, or the rigid frame of an automobile. The process moves from the searing oxygen furnace to the thunderous cadence of the rolling mills. Every step from billet cutting and heating to forging and thread machining must be executed with jewelry-like precision. Giant bolts and nuts complete a manufacturing journey that is calculated down to the smallest detail. The material is ready to move to the next processing phase without haste.